Have you ever really thought about how strange mirrors can be? You have one that shows you the super zoomed-in version of your face and another that shrinks an entire highway into a tiny rectangle. How can one simple thing, a curved piece of glass, show you two completely different worlds? Well, today we're going to pull back the curtain on the hidden physics in your reflection.
I mean, think about it for a second. That shaving or makeup mirror, it curves inward, right? And it gives you this massive detailed view of your face. But then you get in your car and the side view mirror curves outward, and it takes the whole road behind you and shrinks it down to a size you can see at a glance.
So, what's going on here? How can just a simple change in the direction of a curve completely flip the script on what we see? That's the big question, and we are going to solve it right now.
To crack this code, we have to start with the basics. We need to learn the language that light itself speaks. Turns out, light is actually pretty predictable. It follows a few very simple rules when it bounces off of something.
And here's the best part. We don't need to break out some super complex math, at least not yet. We can figure out everything a mirror is going to do just by drawing a few lines, tracing the path of light rays. And to do that, you only need to know 4 simple rules. Think of them as our secret decoder ring.
And these rules just make sense. Look, a ray of light that comes in straight or parallel bounces off and goes through a key spot called the focus. And hey, guess what? A ray that goes through the focus first bounces off and goes out straight. See? It works both ways. Then, a ray that hits the true center of the mirror's curve just reflects right back on itself. And finally, if a ray hits the very center of the mirror's surface, the pole, it just bounces off at the exact same angle it came in at. That's it. With these 4 tools, we can predict pretty much anything.
Okay, so let's start with our first case, the concave mirror. That's the one that curves inward, like a cave. This is the mirror that knows all about magnification.
And wow, this thing is a real chameleon. Just look at this table. Depending on how close or far an object is, a concave mirror can make the image tiny and upside down, it can make it the exact same size, or it can make it huge. It can create a real image, one you could actually project onto a screen, or a virtual one that only seems to be behind the mirror. It really is a shapeshifter.
But for our mystery, let's zero in on one very specific situation from that table. What happens when you put something, say your face, really close to the mirror? So close that it's between the mirror's surface and that focal point we talked about.
Well, the result is exactly what we started with. You get a bigger, upright virtual image. That's the magic behind shaving and makeup mirrors. It's all about that close-up position. And it's the same exact principle dentists use with those little mirrors to get a really good look at your teeth. It's all about getting up close and personal.
Okay, but what if we move things just a little bit? What happens if we place the object, like a tiny light bulb, exactly on the focal point? Well, this is where the concave mirror shows off its other superpower.
Instead of making an image, the mirror grabs all the light coming from that single point and shoots it out forward as a super strong focused beam of parallel light. This is the secret hiding inside your flashlight, in searchlights, and even in your car's headlights. It can even be used in solar furnaces to concentrate the sun's rays and create incredible heat. It's the same mirror, but used for a totally different, powerful purpose.
All right, let's pivot. Time to tackle the other half of our puzzle, the convex mirror. This is the one that bulges outwards, and it's all about seeing the bigger picture.
And whoa, look at how much simpler this is. Unlike its complicated concave cousin, the convex mirror is incredibly predictable. It doesn't matter where you put the object, the image it makes is always smaller, it's always upright, and it's always virtual. No flipping, no magnifying, no drama.
And this right here is the whole reason they're so useful. The big advantage is that they always give you an upright image. You never have to worry about looking in your car mirror and seeing the truck behind you suddenly flip upside down.
And there you have it. That's the solution to the car mirror mystery. Because it curves outwards, it collects light from a huge area, giving you this massive field of view. So you get a wide, panoramic, upright picture of the road. And for driving, that's exactly what you need to be safe.
So we've solved the puzzle with drawings and logic, but you know there has to be some beautiful math that ties all this magic together, right? Well, there is, and it's a universal formula that works for both kinds of mirrors.
This is it, the mirror formula. Now, don't let the fraction scare you. It's just a really clean, simple relationship between the object's distance from the mirror, which we call u, the image's distance, which we call v, and the mirror's focal length, f.
With this one equation, you can calculate exactly what an image is going to look like without drawing a single line.
And there's one more piece to the puzzle, the formula from magnification, or M. This little guy is awesome. It tells us two key things. The number itself tells you how much bigger or smaller the image is, but the sign, whether it's positive or negative, is the secret code. A positive M means the image is upright and virtual. A negative M tells you it's upside down and real.
So come on, let's put this math to the test. Let's take our car mirror. Imagine there's a bust about 5 meters behind it. If we know the curve of our mirror, we can plug these numbers into our formulas and predict exactly what the driver is seeing.
Okay, so you run the numbers through that magnification formula, and this is what you get, plus 0.23. So what does that actually tell us?
Let's break it down. First, the plus sign. Remember our secret code? Positive means the image is virtual and erect. It's upright, just like we see in a real car mirror. Perfect. Now the number, 0.23. This means the image of the bus is only 23% of its actual size. It's much smaller. The math confirms exactly what we knew all along.
So there we have it. We've untangled the whole thing, from simple drawings to the elegant math behind it all. Let's just put it side by side one last time so it's crystal clear.
At the end of the day, it's about two different realities. The concave mirror, the inward curve, is this super versatile tool. It can magnify, it can shrink, it can even flip an image completely around, all depending on distance. But the convex mirror, the outward curve, is a specialist. It does one job and does it perfectly. It always gives you a smaller, upright image with a huge field of view.
So now you know. You've cracked the code. The next time you see your reflection in a security mirror at the corner store, a shiny holiday ornament, or even the back of a spoon, you'll know exactly what's going on. You'll see the rules of light playing out right in front of you. So the only real question left is, where else are you going to spot this hidden science bending the world around you?